Okay, so we're doing 23 right here. 23. Okay, so what's the overall rule you're going to have to use? Like the outside rule. You're going to have to use the chain, but inside the chain rule, what are you going to have to use? You're going to have to use the product, exactly, right. So you're just differentiating this, right? That's what it asks you to do?
Yep.
Okay, so y prime is going to be e to the x cosine x times what? The derivative of what?
The derivative of x cosine x.
X cosine x, the derivative of that. That's correct. So that's going to be e to the x cosine x times, and what rule do you have to use to differentiate x cosine x? Product rule. The derivative of the first times the second plus the first times the derivative of the second. So this equals e to the x, and it stays up there, e to the x cosine x times cosine x minus, oh, x sine x. Thank you. And that's it. You're done. That's it.
Okay, so you...
Another way to more clearly write that, instead of using that little, I can put the little mark that means differentiate. I could take this and I could say times the derivative with respect to x of this, like that.
That makes sense. You take, in terms of e, you take the entire equation and then you take whatever is in the x.
And take the derivative. Yeah, that's correct. Yes.
Okay.
Yes.
There's
actually an ln e on the outside of this, but what is ln e?
1.
1. Remember, the derivative of a to the x is ln a to the x, but in this case, ln e is e. This is another definition for e. We good? Someone pick another one. Someone pick another one.
Can I?
Go ahead, yep.
42.
42?
Yeah. That's the last one.
Oh, cool. Very neat. So it's 2 to the 3 to the x squared.
Is it as straightforward as it looks?
Mm-hmm.
Okay.
So how do you think you should attack this?
Solve for x cubed.
Well, it's 2 to the 3 to the x squared, right? You have to be very, very careful about this. You have to be very careful about this. How do you go about? So this is 2 to that power, right?
Mm-hmm.
So this is going to be, y prime is going to be ln 2 times what? 2 to the what power? 3x squared times what?
Times ln
d dx of what? 3 to the
x squared.
Yes. There's the first iteration of it.
Wait, is it 3?
I am dumb.
Is it 3x squared or 3 to the x to the 2?
3 to the x to the 2.
Oh, okay.
That's correct. That's why I'm keeping this very separate. I'm doing this one exponent at a time. One exponent at a time. So we have ln 2 times 2, because why do we have the ln 2 right there? Because the base is 2. And then what is our exponent? 3 to the x squared. So we need to take the derivative of that exponent. So now if we keep on doing this out, y prime is going to be ln 2 stays there. You have 2 to the 3 to the x squared, right? Times ln 3, correct?
3x squared.
3 to the
X squared.
times what? d dx of x squared. Exactly, Bissell. Very good. You do this piece by piece. So you get y prime is equal to ln 2 times 2 to the 3 to the x squared times ln 3, 3 to the x squared times what?
2x.
2x. And could you clean this up a little bit?
Probably.
Yeah, I mean, you can pull stuff out, but does that communicate to me that you did everything you needed to do?
Yes.
Yeah, it does. Like, you could reorder it. I mean, you might see it like this. Y prime is equal to 2x times ln 2 times ln 3 times 2 to the 3 to the x squared times 3 to the x squared. You have to be careful. You have to be very careful. That is not 2 to the 3 to that power. 2 to the 3 to the x squared power is equal to 2 to the 3x squared. So do you understand why you can't like distribute those in? There's powers of powers would be multiplied together. Be careful. Be very careful. Okay. Someone else pick another one. Record this. So we use the chain rule. First, what would be nice to do before we do the chain rule?
Put it from into power form?
Yeah, so it's going to be x to the 1/2 like this, right? Plus x to the 1/2 like that, plus x to the like that. So y prime is going to be 1/2 x plus x plus x to the 1/2 to the 1/2 all to the what?
-1/2.
negative 1/2 times the derivative of the inside, which is x plus x to the 1/2. Like this, right? That's the inside? That's the inside. Oh, there's a 1/2 right here. Thank you. Correct. That's it, right?
Yeah.
So what's that going to be? It's going to be 1/2. There's a lot of 1/2s there. X plus x to the 1/2 to the 1/2 to the negative 1/2 times 1 plus 1/2 x plus x to the 1/2 to the what power? Negative 1 times the derivative of what?
X plus x to the 1.
Yes, exactly. We're not doing the x plus x to the 1/2 like this. Correct. So there's one last derivative to do. We end up with 1/2 x plus x to the 1/2 to the 1/2 to the negative 1/2 brackets 1 plus 1/2 x plus x to the 1/2 to the negative 1/2 times what? 1 plus 1/2 x to the... Correct. There it is. That's it. It just it explodes. It gets bigger. Yeah. Do it. This is a key tip here. This is really important. The rules themselves, are the rules themselves hard to get your head around? No. Can you combine them pretty easily?
Yeah.
Mostly, right? What was the thing that made this question a little bit more tricky than the other ones?
And so many layers.
Had so many layers. Like, so what would be one thing that would help here? I'd imagine I did this.
Defining different functions.
Well, sometimes kids will do that. They'll actually divide, like, h of x is g of f of x, right? And they'll specifically define. That's totally fine. And that's an example of do each step by step. I see mistakes made all the time where kids do what?
Go right to the answer.
They try to just go straight to the answer, and you'll be able to do that with maybe two functions composed of each other, right? But if something's embedded like this, is it really easy to get a 1/2 in the wrong place?
Yeah.
Yeah, it could really mess you up pretty badly. So do it piece by piece. I mean, did that take very long right there?
No.
Not really. No, not really at all. Simplifying that might be a pain in the butt.
Yeah.
But am I asking you to simplify that?
No.
I'm not asking you to simplify that. It's not much different than doing with two variables, but you need to know some single variable calculus first before you do multivariable. Okay, and this one, let's write this out step by step. So y prime is going to be, can someone tell me what the first iteration of this would be? E to the k tan root x times what?
Times k tan.
Hold on, the derivative of k tan root x. Exactly. What does that k do? It's a constant, so it just, what?
Stays there.
It just sits there. So you can actually take that k and just put it out front if you wanted to, and you're just doing the derivative of tangent of root x. What do you have to use in order to, so y prime is going to be k e to the k tan root x times what? What's the derivative of tangent?
Secant squared.
Is it what? Secant what?
Secant squared.
You sure? We're positive?
Yes.
Yeah.
Secant squared of
Root x
times what?
times the derivative of root x.
The derivative of the square root of x. Exactly. You have to use the chain rule again. So y prime is going to be 1/2. I'll pull it out front quickly. 1/2 k e to the k tan root x times secant of square root of x times x to the what power? Negative 1/2. I pulled the 1/2 to the front. Usually you'd see that actually not 1/2 k. You'd usually see that in a book as k over 2, like that.
Yeah.
And usually the parenthesis would probably be there, if it was there. I like putting the parentheses there to make it absolutely clear what I mean. I put little hooks at the end of my radical signs to show where the radical ends, to be very clear. Are we good on this?
Let me see.
Let's do this. Y prime is equal to 3a squared times the derivative with respect to x of a cubed of a. What's the derivative with respect to x of a? That's 0. I mean, that's like
actually wrote
raw.
that
That's like
out.
terrible calculus that comes out with the right answer. It's
I
0.
wrote that out.
It's 0. It's 0.
Okay.
It's kind of like limits. What do you check first with limits?
Let's see if you can put.
Yeah, is it a constant? It is. It's 0. You'll see that all the time. You will do questions with related rates where you will have things like this. Plus y squared is equal to like 3 squared. And you'll do out the derivative. It'll be 2x, 2y, y prime equals 6. No. No. The derivative of 3 squared is
0.
the derivative of a constant is 0. So far, we've dealt with functions that express one variable explicitly in terms of another, meaning you can get the output just with one input value. Some functions are defined implicitly by a relation. So these will be not functions, they will be relations. Okay, so for example, x squared plus y squared is equal to
25.
What is that? What kind of shape is that?
Circle.
With
4
radius?
5.
Circle with radius equal to 5. Center where?
0.
0 is not a point.
0, 0.
0, 0. Thank you. At 0, 0. That's correct. So if you graph this, 5, negative 5, negative 5, and 5. Let's say I wanted to find the slope of the tangent line at x equals, I don't know, let's say 3. Let's call that 3. Let's say I wanted a slope of the tangent. So just from this rough sketch, what can you tell me about the slope of the tangent line at x equals 3?
It's negative.
It's negative. Okay. We could graph it nicely. Could we come up with a graphical estimate if we wanted to? Yeah, we absolutely could. The problem is, with what we know so far, can we differentiate that?
No.
No, we can't. We need things to be in terms of
X. Well,
x. We need to isolate
Y.
y. We need to isolate y. Put everything in terms of x. So could we isolate y pretty easily? Yeah, we know that y squared is equal to 25 minus x squared. So y is equal to plus or minus the square root of
25.
minus x squared. Now, the positive part of this is the upper or the lower half. Oh, well, the upper half. The negative part is the lower half, exactly. So if we want to find the derivative at 3, if we want to find the derivative of 3 on the upper half, which function do we need?
Plus.
The plus. So we want the upper half. So we end up with y is equal to 25 minus x squared to the what power?
1/2.
To the 1/2. Well, no, we wanted the derivative at x equals 3. 3. 3 was the number we wanted, right? Right here, 3. So y prime at 3 is going to be 25 minus 3 squared to the 1/2. So that's going to be 25 minus 9 to the 1/2. So that's going to be 16 to the...
Wait, you didn't even do it.
Oh, I need to do the derivative. You're absolutely right. Oh, man, fail, huh? Wow, good catch. So if we do y prime, we have 1/2, 25 minus x squared to the negative 1/2. I'm done.
No.
No, I'm not. Oh, man, I'm not done. What do I need on the outside?
2x.
Negative 2x, not 3x?
No, 2x.
2x or negative 2x?
Negative 2x.
Negative 2x, good. We can clean this up a little bit. We end up with negative x times 25 minus x squared to the... Ah, so now can we do y prime of 3?
Yeah.
Yeah, what's y prime of 3 going to be? Negative 3 times 25 minus 9 is? To the negative 1/2. What's 16 to the negative 1/2? 1 over 4. So this is going to be negative 3/4. Does that match reality, or the reality we hoped?
Yeah.
Yeah, does negative 3/4 match kind of our graph up there?
Looks like it.
Absolutely. Let's say we wanted the slope right here, going at 3, but at the bottom arc. What would you change? What's the only thing you would change?
The negative sign.
The negative sign. So that would actually be 3/4. This slope is negative 3/4. Okay, that's nice. That's really fun, right?
Sure.
Sure? That's really fun. Now, what happens, though, if I just change this equation a little bit? What happens if I made it x squared plus, I don't know, xy plus y squared is equal to 25? Our method was, what was our first target? We need to do what first?
Isolate Y.
Isolate y. Is it theoretically possible for you to isolate y here?
Theoretically.
Theoretically, yeah, it is. It is. Does it become really nasty really quickly?
Yeah.
This is really not cool to isolate y in this one. Really not cool. Do you agree?
Yeah.
Yeah, I really don't want to do that. Okay, so let's go back to our original one where we could isolate y and just see if we can find out a different way of doing it. What was our original question? Our original equation was x squared plus y squared is equal to 25. Do you agree that y is some function of f of x? Do you agree with that?
Yeah.
It is some function. So let's say this, x squared plus f of x squared is equal to 25. Let's differentiate this whole thing with respect to x. What's the derivative of x squared with respect to x? 2x. If we differentiate this with respect to x, we end up with 2 f of x times what? Yeah, f prime of x equals what? 0. The derivative of 25, it's a constant, is
0.
This is exactly what I just asked you to watch out for, okay? I'm trying to kill this right now. Because the downstream work, if you keep that equal to 25, what happens to everything else?
You die.
Explodes you. It's not nice. What are we interested in isolating?
F prime of x.
Yeah. So I'm going to divide by 2 first. Right? So what does f prime of x equal? Negative x over f of x. What was f of x? F prime of x is equal to negative x over
Y.
Over y. So we wanted the slope at x equals 3. So to find the slope at x equals 3, what do we also need?
Y.
Y at what?
3.
When x is 3. We know that it's x squared plus y squared is equal to
25.
25. So when x is 3, if 9 plus y squared is equal to 25. What does y equal?
Wait,
Plus or
what's the equation we were using?
Yes, that's the original one. X squared plus y. Oh, yeah, x squared plus y squared is equal to 25. Yeah, y equals plus or minus 4. Now we wanted this one, right? So what? It's positive, right? So we wanted 3 comma 4. Well, we take 3 comma 4 and plug it in there. F prime at 3 comma 4 is going to be negative. Is that the same thing we got before?
Yeah.
Yeah. Did we? What's the key thing we didn't do? We didn't have to what?
Isolate Y.
We didn't isolate y. We did not isolate y. We did not isolate y. So this is called implicit differentiation. We are essentially differentiating without isolating the y. If we isolate y, we have the explicit form of the relation. It might be piecewise, though, because is this a function right here, this circle?
Nope.
No. How many functions is it? At least. At least 2. At least 2. It's a relation. Okay, so let's try and...
Well, whatever the kind of the
Origin.
no.
The origin is a point we know it goes through. That's correct. But what might be another point?
The thing that it
Yeah.
it
Upper right, maybe?
Yeah,
Yeah,
that thing.
you know, this might be an interesting point to find. It's not so I mean, you can figure that out. It's not so trivial, but it's kind of a neat point to think about. The point is, let's say we wanted to find, I don't know, the slope of the tangent line at 1, when x is 1. So we want the m at x equals 1. Now, looking at this, let's say I asked you to isolate y. What's the problem with isolating y on that one?
it has no friends.
It has no friends. How many times is y written in that relation?
Twice.
Twice. So that's the first danger thing. But also, what power is y being raised to? The highest one is cubed. Is that something that can be nasty to deal with?
Yeah.
Yeah, absolutely. There is a cubic equation you could use. You know, you'd find the positive root, blah, blah, blah. Is it really nasty to break this apart into 3 functions?
Very much.
Very much so. So instead, what are we going to do? Implicitly differentiate. So what was that? It was x cubed plus y cubed equals what? 6xy. We're going to differentiate with respect to x. So the way you can think about this is y is equal to f of x cubed plus f of x cubed equals 6x times f of x. Let's differentiate with respect to x. What do you end up with? What's the first thing you end up with, Jackie? What's this? What's the derivative with respect to x? Yes? Plus, Maddie, what's the next one? This one. 3f of x squared times what? Yes, f prime of x equals what rule Bissell do you have to use on the right hand side of this? What rule do you have to use? Product rule. The 6 just sits there. The derivative of the first is, what's the derivative of x? 1 times f of x plus the first times, yeah, exactly. But now what do we need to do? Isolate f prime. Ready, everybody? Please isolate f prime right now. Do that by yourself. What do we do to simplify this? You could stop there, or you could say f prime of x is equal to 2y minus x squared all over y squared minus 2x. Either one is fine. That's what I would do right there.
Because there's only one value for each x.
Exactly. X, just the x uniquely said this one point, but on something that's it's a function, exactly. By definition, it has one output. But here it's a relation, could have more than one.
Whatever.
Yeah, in this case, how many are there? Could there be?
3.
It could be 3, right? There absolutely could be 3. Another way to think about this, you might be able to use is how, what's that x value right there, where you get a horizontal tangent, It's one thing you could ask for. But the point is, why do I have you substitute an f of x for y? Are you going to have to do that? No, you're not going to have to do that. You just need to remember, you could do this entirely without substituting f of x for y. Just remember that what's the derivative of y with respect to x? Y prime. What's the derivative of x with respect to x? 1. It's invisible, 1. You need to make sure you kick out that derivative, that y prime. Putting in f of x forces you to think about that. So you don't have to, as long as you remember the derivative of y with respect to x is y prime. What's the slope of the tangent line at 3, 3? That's as simple as plugging in 3 and 3. You end up with 6 minus 9 over 9 minus negative what? Negative 1. Hey, that's nice. Okay, where's the slope? Where's the tangent line horizontal? The tangent line is horizontal when the slope of the tangent line is 0. So this is really important to do. So we know this is the derivative. So what has to equal 0 for the tangent line to be horizontal?
2y minus x squared.
2y minus x squared has to be 0. So you know that 2y, this is when 2y is equal to, so that's when y is equal to x squared over 2. But what other thing does it have to be? It has to be when y equals x squared over 2, but also when what? What's the original equation? X cubed plus y cubed is equal to? Both of these things have to be true. So if both of these things have to be true, what do we do to solve?
Set them equal to each other.
We can't, not setting them equal to each other. You know y is equal to x squared over 2, so what do?
Substitute x squared over 2.
Yeah, and you get x cubed plus x squared over 2 cubed equals 6x times. All we're doing is plotting the intersection. How many variables do we now have?
1.
1. So we have x cubed plus x to the 6th over 8 equals 3x what? Cubed. So you know that x to the 6th over 8 is equal to 2x what? Cubed. What's one of the answers that you definitely have? X equals 0. That's correct. Let's be careful about this. So if we divide both sides by x cubed, what do you end up with? X cubed over 8 is equal to 2. So x cubed is equal to 16. So x is equal to the cube root of 16. The cube root of 16. Now let's just... No, it's an odd root.
Oh, right.
16 to the, just so you get this 1/3, is, so just so you know what this is about 2.51984, like this, and it keeps on going. Let's see if that visually matches here. We're trying to find where the slope of the tangent line is horizontal. Here's the original graph.
Yep.
You sure?
That looks like the tangent
0
line is
works, right?
vertical.
Yeah.
0 right there, right?
Yeah.
Well, let's look at this graph here. We said we found these, when we solved this, it was the cube root of...
That looks wrong.
Something looks wrong here because it's 2.518, but look, 2 is right here. Does the function even go out to 2?
Nope.
It should be like, it looks like it's 1 point something, right? Like 1.25 something. So let's just take a look, see what we did wrong. There's a mistake somewhere. Our algebra is correct. The graph actually looks like this. And does that actually work? Yes, it does. It absolutely works. It's right here. And that is the cube root of 16. So this graph is not accurate. My guess is that for this graph, it's 3xy. That's my guess. That's my guess.
Yeah.
Okay, moving on. Here's another one where isolating y really hard. We have two y's. Y's on the inside and on the outside.
Oh, you're gonna have to do.
So, do you even attempt to isolate y?
Nope.
No. Okay? It's not that bad, and we won't have to substitute on this one. So, what's the root of sine?
Cosine.
So, this is cosine x plus y times what? 1 plus what? Y prime equals, what do we need to use on this? What rule?
Product.
Product rule. The derivative of the first is 2y y prime times negative sine x plus y squared times what? Negative what? Negative cosine x. Exactly. If we wanted to find y prime, what would we need to do right now? We're not done. What would we need to do? What did I have you do on the last problem?
So we'll isolate
Y prime. Yeah, you could isolate y prime. Exactly. If I asked you to find y prime at a certain value, do you need to isolate y prime first? No, because think about this. If I isolate y prime now, I have to deal with x's and y's and all sorts of funky stuff like that, right? If I just find y prime at a certain value, look, is y prime in there?
Yep.
Is x and y, are x and y's in there?
Yeah.
Yep.
Could you substitute numerical values in first?
Yes.
You could. Is that sometimes a lot easier than isolating y prime?
Yeah.
Yeah.
So always ask yourself, do I need to isolate y prime? In this case, if the question was just asking what is y prime, what do you need to do at this point? You must isolate y prime. But if I was asking you what's y prime at, x is pi over 2, y is pi over 3, my guess is that the trig values will be really nice. So instead of moving around cosine x plus y,
Just put in the
you plug it in. It's like root 2 over 2 or something like that. Yes, Sam.
When you tell us to find the derivative of,
You have to
want us
isolate. You have to isolate,
Okay.
yes. If I asked you to find the derivative, you would have to isolate, exactly. So let's figure this out here. So let's differentiate with respect to x. What rule do we have to use right there? Product rule. The derivative of the first times the second plus the first times the
Derivative of the
equals 0. 0, 0, 0, 0, 0.
I think
2x minus 2y what?
prime.
Y prime is equal to?
0.
0. So what is this? X minus y prime is equal to 0. If we isolate y prime over here, x y prime is equal to negative y. What does y prime equal? Negative y prime over x. Exactly. And over here, what do you end up with? Negative y prime is equal to negative x. So what does y prime equal?
X over y.
X over y. At any point on this function, the slope of the tangent line is negative y over x. Do you agree with that?
Yeah.
At any point on this other function, the slope of the tangent line is x over y. Does it matter what c or k is?
No.
Doesn't matter what they are. That's always what the slope of the tangent line is, correct?
Yes.
What's negative y over x times x over y? Negative 1. So wherever these intersect, the intersection lines, the slope of the tangent lines will always be what?
Perpendicular.
So these are orthogonal families of curves. How many different curves does this represent? As many as you want. Does it matter what k is? Does it change the derivative at xy? No. Does it change the derivative over here?
Nope.
No, it does not. It absolutely does not. So have we proved that do these intersect? Well, they could intersect many, many different places, but we have proven if they intersect, everywhere they intersect, the slope of the tangent lines are perpendicular. So these are orthogonal families of curves. Why are they a family of curves? How many curves does this describe? Many. How many curves does this represent?
Many.
And there is a relation between them. They relate because they fit this form. It's a family of curves. So to prove that two things are orthogonal, two tangent lines are orthogonal, two lines are orthogonal, you multiply the slopes together, and if they're negative 1, they are
Perpendicular.
If they're not negative 1, it's not perfect. There's no way around this. This is the first thing which I think is kind of nasty, that I'm telling you right now, you must memorize the derivatives of inverse trig functions. You must. You must, you must. You must, you must, you must. You must. This is not, I guess, totally make or break. I think it is possible to pass the AP exam without memorizing this, but it'll cripple you and make it very hard to succeed at a high degree if you don't. 6 things to memorize. It's not that bad. It's really not that bad. I'm not going to differentiate it at the moment. It's in your notes. It's in your book how they get them. Here they are. Here they are. The way you prove these, it's pretty straightforward. You do the derivative of sine, and then guess what? The inverse sine, the derivative of inverse cosine is similar, and then all the other ones are written in terms of sine and cosine. So what can you do directly? You can then do them directly. Here they are. I'm going to say this on the record and in here. Memorize these. They're not, no, and
they all relate in some
that's one thing that makes it easy to remember them and makes it hard. People mix them up. Here's one thing I will point out. Anything, where is it? all of the, which ones are negative? Let's look at where the negative signs are. Here's a negative, and here's a,
It's all the cos.
anything that begins with C is going to be,
Negative.
that's one thing to remember. The forms are very similar, just be very, 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 very careful. You must memorize these now. Now. So now we're differentiating with respect to
Y. Well,
x of sine y.
Yeah.
The derivative, and we put it on the other side, so the derivative of x is 1. The derivative of sine y is going to be cosine y times
The derivative.
dy dx. Exactly. Dy dx is therefore equal to 1 over cosine y. Exactly. We know that sine squared plus cosine squared is equal to
1.
Do you agree with that?
Yes.
So therefore 1 minus sine squared has to equal cosine squared. Does it matter what variable we call that? What I mean by that is sine squared y plus cosine squared y is equal to what?
1.
1. So what does cosine squared y equal to? 1 minus
Sine squared y.
sine squared y. Do you agree with that?
Yes.
So what does cosine y equal?
Root of
1 minus what? Sine squared y. Do you agree with that?
Is it plus or minus?
It's plus or minus.
Okay.
We're going to fudge this a little bit right now. We're looking at the principal root.
Okay.
This is not the super complete proof. Are you okay with me so far?
Yeah.
Yes.
But what do we know x equals?
Sine y.
Sine y. So what does cosine y equal in this case? The square root of 1 minus x squared. And that's what goes right there. And that's how you get 1 over 1 minus x squared. Do I expect you to be able to pull this out? Not really, but you need to know to prove the derivative of inverse trig functions, you will need to differentiate implicitly.
You won't have to do proofs on
No, not like this, but as part of the work. I mean, saying you're
Yeah.
proving things all the time, like
Yeah.
show that the derivative. I mean, what's the difference between proving and showing your work? Nothing. There's absolutely nothing different. Once you have cosine and the derivative inverse sine, the inverse cosine, can you do all the other ones?
Yeah.
Yeah, you can. They all come. You must memorize these.
It just takes a bit of lateral thinking, but
This is like the definition of lateral thinking, exactly. You can follow the same thing, but what's going to pop out? Some negative signs, right? Because the derivative cosine is negative sign. Hey, look, all those negative signs pop up. Do the denominators change a little bit? Absolutely. You must memorize these. It's really, really, really important.